So I made a deal with the organizers that I'm giving only one lecture, but I'm allowed to use PowerPoint, which is a big no-no in the other lectures. And I can't run too much overtime because the grocery buses leave at 5:25, so I'm in a rather constrained spot. And then another announcement in my capacity as an organizer is that there is a slight change in tomorrow's schedule. It's just a permutation of the first two lectures. So Daniel Jeffers will speak at 9:30, and then Greg Moore will speak at 11:15. So the same set of speakers, just a minor permutation. About the title of my series of one lecture, many people were puzzled by it, but it just turns out to be one of these silly brain jokes, like brain scan and brain surgery, etc. But it's actually this whole idea of generalizing ADS-CFT correspondence by considering stacks of brains on cones, at least has played a big role in my life because I've been working on this for now something like a dozen years. I wish some of this stuff that I'll talk about were more recent, but anyways, I'll do what I can. So just a very brief reminder about how ADS-CFT comes about from D-brain or M-brain motivation. We know that one way to embed n equal 4 super Yang-Mills into string theory is to consider a stack of parallel D3 brains. This is actually not how it was originally derived. Maybe some of you don't know that n equal 4 super Yang-Mills is really a creation of string theorists. I think it first figured in a paper by Brink, Shirk, and Schwartz. And basically they realized that the effective action of type 1 theory in 10 dimensions is just 10-dimensional supersymmetric Yang-Mills theory. And then they had the idea to compactify it down to 4 dimensions, and out popped this wonderful theory that has been very much probably the dominant subject of this school. So in those days it was like a toroidal compactification, but then when D-brains kind of started to be appreciated in the mid-90s, people very quickly realized that if you stack n D-brains parallel to each other, you get UN maximally supersymmetric Yang-Mills theory. On the other hand, you can certainly think of these D-brains because they have 6 dimensions which are transverse to the brains. You can then think just about the curved 10-dimensional space, line plus 1-dimensional space, which lives, roughly speaking, outside the stack of brains. And then, can you hear me well? Yeah, there was some sort of echo. Okay, so a schematic picture of this warped space is this flat is this kind of semi-infinite throat, which is denoted here, which opens up into flat 9 plus 1-dimensional space. The reason this is pictured as a throat is because if you look at this well-known extreme metric of D3 brains, there is a warp factor in front of the transverse 6-dimensional space, which works in such a way that the radius of this, the radius of the 5-sphere actually doesn't shrink as you go to r equal to 0, because there is a cancellation of L squared over R squared and this R squared. So all you get is just a decoupled 5-sphere of some radius L, which can be made very large in a certain regime. And then the remaining coordinates are the 3 plus 1 warp directions and the radial variable, which neatly assemble, it's easy to check, into 5-dimensional ADS space. In this case, it's just a Poincaré slice of the 5-dimensional ADS space. So basically, there are 2 ways to view the theory of brains at low energies. One is via the gauge theory that lives on the brains, roughly speaking, the open string sector. and the other one is the closed string theory that lives in this warped space. And at low energies, there is a kind of decoupling between the region far down the throat and the asymptotically flat region. And this is, in a nutshell, how ADS-CFT correspondence is motivated via D-branes. This is motivation, not a proof, but in all cases where we know how to construct a precise duality, we essentially do it via these kind of brane constructions. And the other thing that I think already figured in many talks is that if you compute the radius to the fourth power, the radius of curvature of ADS 5 crosses 5, and express it in terms of the string scale alpha prime, you find this factor G Young-Mills squared n, which is the 't Hooft coupling. So when the 't Hooft coupling is large, the space is weakly curved, and you get a reliable description of a strongly coupled n=4 theory via weakly curved gravity. Okay, so another thing that keeps cropping up is that n=4 super Young-Mills is a really special theory. It's a theory which has a kind of maximal superconformal symmetry group, and probably also this exact integrability that we heard about in Juan's and Pedro's lectures. But if you, so sometimes we think of n=4 super Young-Mills as a kind of distant cousin of QCD, which is cleverly arranged in such a way that the beta functions exactly cancel. So in particular, if you take this SUN or UN theory, there are 6 adjoint scalar fields and also 4 wild fermions interacting with the coupled to the gauge group. And then, for example, you can easily do a one-loop beta function cancellation, and you see that the beta function exactly cancels for this matter content. So unlike QCD with a small number of flavors, this theory doesn't have a beta function. And moreover, this fact actually persists to all orders and non-perturbatively. So there is a kind of fixed line. You can, while in QCD there is dimensional transmutation, and instead of thinking of dimensionless G Young-Mills, you think about some QCD scale lambda. In n=4 theory, you can actually dial G Young-Mills to any value from 0 to infinity, and the theory is superconformal for any of these values. And the idea is to try to solve for various physical, quote-unquote, physical quantities as a function of this coupling. So I don't need to say much more about this because this was reviewed a lot in the previous lecture and other lectures at the school. But then, so one of the interesting things that questions that is raised by this duality between n=4 super Young-Mills and ADS 5 crosses 5 is whether this gauge gravity duality is something restricted to very few theories, or there is some large class of theories to which similar methods apply. And here these cone-brane dualities come in very usefully because they almost immediately provide a set of generalizations which break supersymmetry. So the idea is to, instead of starting with just flat space R9, 1, you replace 6 transverse dimensions instead of just flat R6, you replace them by some Ricci flat cone. So you have this Ricci flat 6-dimensional cone, and then you have the 3+1 directions of the world volume. And then you basically fill R3, 1 with some number of D-branes, positioned either right at the tip of the cone or somewhere, perhaps somewhere else. But the simplest reason to see why it's different is to put it at the singular point, the tip of the cone, and clearly there you expect that the theory is going to be different because you kind of put it at this singularity. Then on the gravity side, the construction is going to be pretty much the same as what we had before. If we go back to this metric that we saw here, you write exactly the same type of metric, except now this dr squared plus r squared d omega squared, you think of it as a cone metric. And then d omega squared is the metric on the base of the cone. then you play exactly the same game, and instead of ADS 5 crosses 5, you find the metric, you still have ADS 5 times the metric on the base of the cone, which turns out to be the Einstein metric, namely its Ricci tensor is proportional to the metric G mu nu. This is a general property of a cone, that the base of the cone will be an Einstein space. So you basically change the metric by replacing these compact 5 dimensions by some other type of space. And then the field theory changes as well. It becomes some other theory with generally broken supersymmetry, because just to begin with, the cone preserves fewer supersymmetries than flat space. For example, if the cone is a Calabi-Yau space, then you only have 1/4 of the original supersymmetries, namely 8 instead of 32. So then there is another set of interesting effects. It's still true that the radius is G string n, but then there is some subtle factor of 1 over the volume of the base of the cone that actually plays some role in precise checks of this duality. So the generalized duality then will be that this gauge theory on this stack of ND branes is conjectured to be dual to the infrared limit. It's conjectured to be dual to ADS 5 cross Y. Okay, so now just to explain how it works in probably the simplest conical examples, we can take the cone, which is locally R6, but it's just modded out by some discrete orbifold group. So you know that R6 has the obvious, if you pick a point, it has an obvious SO6 rotation group around this point. And SO6, as we heard many times, is isomorphic to SU4. SU4 is the action on these 4 complex Weil fermions, or on the supersymmetries. And then you just take gamma to be some discrete subgroup of this SU4, which acts in a certain way. And then there is a certain projection you can do on the n = 4 theory, which removes some of the fields. So usually one can rather explicitly discuss, for example, ZK orbifolds. And the action for these ZK orbifolds usually works in this way. There is a bunch of phases like e to the 2 pi I x1, x2, and x3. And this whole thing is an SU4 diagonal matrix. So the product of these 4 phase factors has to be equal to 1. So this action of the orbifold on the fermions is specified by 3 integers mi. So each of these xi's is mi over k times some n. And then there is a very simple way to see which part of the supersymmetry these orbifolds preserve. For example, if none of the eigenvalues of this generator is 1, then there is some action on every single supercharge, and then all supersymmetry is broken. If one of these eigenvalues is 1, then n = 1 supersymmetry is preserved. And if 2 of the eigenvalues are 1, then n = 2 supersymmetry is preserved. And one can construct some simple examples of each of these orbifolds, n = 2, n = 1, or completely broken supersymmetry. Okay, and then one can also construct, once you know that the action in SU4, you can easily construct how the action acts on the vector of SO6, namely on the 3 complex coordinates of the C3 space, which is transverse to the brane. If you think of 3 complex coordinates, Z1, Z2, and Z3, and their complex conjugates, Z1 bar, Z2 bar, Z3 bar, you basically see that this action in SO6 will just be determined by some of these m's. Namely, you just take 4 times 4 of SU4 and you get the antisymmetric product. And then you get SO6 action. So these phases are M1 plus M2, M1 plus M3, and M2 plus M3, and they're complex conjugates. Now here there is another immediate observation that if none of these phases equals 1, then the orbifold acts freely on S5 mod gamma. Namely, if you look at the set of points some distance from the origin, namely you exclude the origin, then you see that on this space S5 mod gamma, all points move around and no points are fixed by this orbifold action. The tip of the cone is by construction a fixed point, but we noticed before that the tip of the cone is kind of removed when you take the near horizon limit, right? Because it just becomes part of the ADS space. So that we don't care about. But we care about whether the action on S5 mod gamma has fixed points or not. And for example, a very well-known example of a supersymmetric freely acting orbifold is the Z3 orbifold, where you just take all three of these mi's equal to 1. So if you, for example, take this to be e to the 2 pi I over 3, these three, and then this is just equal to 1. So because it's 1, you see that you preserve n equal 1 supersymmetry. And this orbifold, the field content of this orbifold, which I'll explain in a moment how this comes about, the gauge group is UN cross UN cross UN, and there is a chiral field content. There is a bifundamental, so each of these arrows represents a chiral superfield, which is fundamental with respect to this gauge group and anti-fundamental with respect to this one. And you see that the matter content is chiral because the arrows point only in one direction, and there are 3 arrows this way, 3 arrows this way, and 3 arrows this way. So how do we see this field content? Well, this goes back to the work in, I believe, in '96 by Douglas and Moore. They found a set of rules for how to project. So if K is the rank of this discrete group gamma, they figured out how to make a projection of the gauge theory that gives us basically what we want, a candidate superconformal field theory. You start with bigger gauge group U and K, and then you accompany the action on the fields by these phases, these twist phases like e to the 2 pi I x1, e to the 2 pi I x2, by also a conjugation in the gauge groups. And this conjugation explicitly breaks the U and K gauge symmetry down to U n to the K, because the whole n by n matrix consists of blocks, and say in the first block is just the identity matrix, and the second block it's still diagonal, but it's identity times e to the 2 pi I over k, and so on. And then so when you look at this field content of U and K, of nk by nk matrices, you only pick out the parts which are left invariant by these combined transformations. And then you're done. So this is a general set of rules, and I suggest that you play with it and, for example, derive how this matter content for the Z3 orbifold comes about. In particular, you should be able to see that the spectrum of fermions completely agrees with the spectrum of scalars, and therefore supersymmetry is unbroken. But this is not guaranteed to be the case. So more generally, if there is completely unbroken supersymmetry orbifold, then the scalars and fermions are not going to be commensurate with each other, and you get some kind of non-supersymmetric field content. For example, let me just flash for you one example of such fancy quiver. This is a Z5 freely acting orbifold, and here these white arrows are fermions and the black arrows are scalars. So you see that the representations of the fermions and of the scalars are different in this case, and supersymmetry is manifestly broken. So this is the typical sort of situation that you're going to get. And then, so the feeling, soon after these orbifold papers were written, people thought that we have a lot of candidate large N conformal field theories. Because, first of all, one way is to conjecture that they're conformal is that they appear to be dual to ADS 5 crosses 5 mod gamma, right? And usually when there is ADS 5 around, we say it must be conformally invariant, because in ADS CFT, the geometric symmetry of ADS 5 space is mapped to the SO4, 2 conformal symmetry. However, it turns out that there are some important effects which this sort of naive argument overlooks, which raise a lot of questions about the cones which break all supersymmetry. In other words, about non-supersymmetric orbifolds. And the way it works is that so people pretty quickly managed to prove that the beta function for the gauge coupling in this orbifold theory, and also other so-called single trace beta functions, are all zero. And this was possible to prove in general whether the orbifold is supersymmetric or not. However, in the initial analysis, people did not analyze in detail the marginal double trace operators. Because if you have a field theory, to check that it's conformal, you have to check that all marginal operators don't flow, all marginal couplings don't flow. And since all these theories have scalars, you can write down lots of quartic scalar operators. And in the initial analysis, people were not so careful. I mean, they realized that they may pose trouble, but it wasn't totally clear how much attention one has to pay to this potential trouble. And then at some point, a few years ago, Anatoly Demarsky, who I think is here somewhere, Rado Roiban, and I decided to analyze these double trace beta functions in more detail, just to see are they really troublesome or not. Because, for example, an optimist could say, even if there are beta functions, they could just all flow to fixed points, and the theory could become conformal in a kind of more interesting and non-trivial way. And what we found is the following, that in general, what gets induced are so-called twisted double trace operators. Namely, it's a product of single trace operators, but each of these transforms non-trivially under the, say, ZK orbifold group. And this is what this label N means, that it's in some non-trivial twisted sector, but the net operator On times O minus N is untwisted, and it surely gets induced. And we found the following one-loop expression for the beta function of F. It turns out that there was some coefficient times 't-Hooft coupling squared, then another coefficient times F times lambda, and then finally some coefficient F squared, which we can set to 1 by just rescaling F in principle. And from here you see that even when F is 0, there is this term which kind of induces this operator, even if you assume that it's not there at tree level. I also want to say that it actually is there at tree level, which is another important fact. So basically one then has to look at this, and this looks like a pretty simple enough expression. Incidentally, it's exactly the same as in the classic Coleman-Weinberg paper. Even though they didn't deal with the large N theory, they dealt with, say, scalar QED, and they obtained exactly the same type of expression. Yes?
So what is this 1D A depend on?
A is just a coefficient which needs to be computed.
So is it a function of N? Or?
Yes, it's a function of N, and it's a function of K of the orbifold. Everywhere. Yeah. Yes.
Isn't the case that multi-trace operators are suppressed by factors of 1/n?
Good. I knew someone would immediately ask this. This is part of the reason why maybe people didn't worry about this so much. But I don't think they're suppressed. And for example, if you look at the normalization, so for example, the VEV of a single trace operator in a standard convention is of order n. Then the standard Yang-Mills action is of order n squared, because there is 1 over g Yang-Mills squared times trace f mu squared. So just a classical action is of order n squared. Now suppose you just add a double trace operator f on o minus n, where f is of order 1. Then on in this counting is of order n. So this gives you exactly the same leading n squared contribution as this term. So basically, they do change the leading planar energy. And this was basically known to anyone who worked on like matrix models, and because sometimes you can just add double trace terms which create non-trivial effects only at leading order. Well, I used to do these type of things in my youth. So now, in fact, just to make it perfectly convincing, the following interesting effect arises, that basically if you start with this UKN theory and make the orbifold projection, you really, to begin with, you get UN to the K with a bunch of U1 factors. But these U1s have charged matter. So dynamically, they actually flow, what I call globalize. There is globalization of symmetries. And this kind of globalization you can't demonstrate against. It's really there in the theory. What happens is that there is some U1 gauge coupling, and we know that far in the infrared, these U1 gauge coupling just flow to 0. After you go through this process of globalization, you realize that you basically have to, that the theory is not exactly the same as the one you started with in the UV. And this particular theory has a potential which explicitly contains double trace operators. So in other words, you start with the UN to the K theory without double trace operators, then you flow the U1s to 0 coupling, and you end up with rather explicit double trace terms. So they're actually there. If you carefully sit and write down what the potential of this CFT is, it contains double trace terms, which are important. They contribute on the same order. And this is true whether the theory is superconformal or not. But the big difference arises in just the dynamics and the form of these beta functions. So we decided to just investigate in detail what are these coefficients A and gamma are for essentially all orbifold theories. And then the crucial thing is whether there is a real solution for f. Because if this quadratic form has a discriminant that's less than 0, then there is no fixed point. But if it has discriminant bigger than 0, then f just flows to a real fixed point. So my hope originally was maybe all discriminants for all the operators are positive, but this hope gets dashed by explicit calculations. In fact, one can essentially prove that there are no orbifolds which are without supersymmetry which have fixed points at one loop. For example, if you look at a class of ZK orbifolds which have SU3 global symmetry, namely 3 of the phases are the same and the 4th one is different, and then you essentially plot, then there is a bunch of these operators which with labels n. For example, for Z5, you see that there are O1, O minus 1, O2, O minus 2, things like these. And if you send K to a large number, then there will be lots and lots of these sectors. The number will go up to some large number, these labels. And then you can plot the value of the discriminant as a function of this. So in the limit of large K, this becomes like a dense set of points. And you see that there are always operators with negative discriminant and also some with positive discriminant. So in particular, this Z5 orbifold model, which I think people even tried to use for conformal unification or something like that. That actually is not conformal at all at weak coupling. These couplings do flow, and you end up with some points sitting in the negative discriminant region. So these are perfectly conventional quartic operators, which cannot be ignored in this theory. So then, so we essentially came up with the conclusion that so at least at one loop, there is no theory that would pass a conformal field theory test if Coleman and Weinberg sat down to compute, or field theorists in mid-70s who knew these techniques sat down to compute whether beta functions are zero or not. And the crucial thing is that you need to check not just single trace, but also these double trace beta function. Yes? No, the beta function is a beta function.
But if it's not a coupling, presumably the CFT.
Well, the tuning means that you have to go and find the zero of the beta function, right? That should happen dynamically. But once you computed the beta function, that's an invariant thing, right? You've isolated all the logarithmic divergences, and you have to check that. So one good news is that if you take the C3 orbifold, which I started with, that actually works in this way. Like, what happens is that for supersymmetric orbifolds, there are couplings whose discriminant is exactly zero. Namely, this beta function is a perfect square. It's something like f plus a lambda all squared. And then you can just say, here is my fixed point, f equal to minus a lambda. That happens to exactly agree with your with your action, with what you see in the action. So it turns out that the action contains these double trace terms, but they're automatically satisfying the zeros of the beta function. But for other things, they just flow away. There is no real zero. They just start heading out of your region of control. And then one can ask, what about higher loops? So in fact, a couple years ago, there was an interesting paper by Pomoni and Rostelli who showed that actually to all orders in lambda, the following expression still works. It's still quadratic in f, and these are just some non-trivial functions which no one has even bothered to compute the two-loop corrections to these functions. And then this raises the hope that the form of these functions is such that while we basically showed that at very small lambda, there is no CFT, there is no fixed line, but it could appear for lambda bigger than some lambda c. And this is actually also suggested by dual string theory arguments, because as you make the dual S5 mod gamma large, there are arguments that these twisted sectors pick up large anomalous dimensions because they're dual to highly stretched strings. And then, so that was kind of a lure, but we don't know if this is completely foolproof or not. I think it would be very interesting if some more control is gained over these functions. And then finally, in the region of strong coupling, some other type of instability was found by Horowitz, Polchinski, and Orgera, which is a kind of non-perturbative tunneling instability, which is only possible to see on the gravity side. So essentially, one thing we know is that if these series are conformal, they might only be conformal at some intermediate coupling. There is definitely no fixed line passing through the origin. That's basically what our one-loop study said. And upshot is life is hard without supersymmetry. Yes?
Excuse me, what is the argument to go to all order when they derive this?
Just analysis of graphs. One just shows that there is no term like f cubed, and that can be done just from the fact that these f's multiply double traces. So the crucial thing is that all these terms are of order 1. So the rate of flow is of order 1. We're dropping terms of order 1 over n squared. So there is a term like f cubed, but it's suppressed by n squared. So we're just working at the leading large n level. And the crucial thing is, even at the leading large n level, the beta function for these order 1 couplings are all of order 1. So there is no sense in saying that these series are quasi-conformal by any stretch. Everything flows fast, and whoops, these series just run into trouble right away. And one comment I wanted to make is that this is not something I had time to describe, but the reason the original cone-brain argument kind of might fail in this case. So let's go back to this beautiful picture. Cone-brain picture, you stack brains at the tip of a cone, but in this particular case, the cone to begin with is unstable. Unstable because if you just look at the spectrum of closed strings localized at the tip of the cone, there are tachyons in here. And this turns out to be the case for all non-supersymmetric orbifolds. And when there are tachyons, it means that cone dynamically wants to smooth itself out. And this kind of suggests that this will become a smooth point. And usually brains placed at a smooth point are really like n equal 4 super n mils. So this gives you a heuristic argument that these theories might all just flow down back to the maximally supersymmetric case, which would be a somewhat disappointing conclusion because we were hoping to find lots of non-supersymmetric CFTs, and we don't seem to be finding them. But this doesn't completely settle the issue. And if you are just a field theorist, you would be interested in, for example, studying what the structure of these functions is. There is hope in doing that because perhaps integrability techniques could help us with something like this. Okay, so this is the adventure with completely broken supersymmetry in cone brains. And you see that it's much harder. So in the next step, I will just drop back to n equal 1 supersymmetric theories and show you that there one can actually do a lot of things reliably without worrying about any instabilities. Are there any questions about this part of the talk? So this part of the talk was largely just doing good old one-loop computations of beta functions and trying to see how to square it with what you see on the string theory side. And as I mentioned, if you read some of the papers I mentioned in the reading, you see that there is a pretty detailed match between the existence of instabilities of the cones themselves and the existence of the instabilities of these double trace couplings.
Igor, does this also invalidate the various claims that you could use these parent-daughter equivalences to say things about non-supersymmetric theories about the strong elements of non-supersymmetric theories?
It might. I mean, for example, for one thing, the Z5 model, I think people tried to use it for so-called conformal unification. Like there was the idea that, and that I think just runs into trouble because the theory is not in any sense conformal. So, right.
The apparent daughter statement was only for single trace operators.
Exactly. For single trace untwisted operators, it's fine. Unfortunately, when you sit down to compute, you see these operators which are untwisted being generated, but they're products of a quadratic in scalars twisted one and quadratic in scalars with opposite twist, exactly like O and O minus n. And that's basically what you run into, and it's trouble. There may be some way around it at intermediate coupling, but it's not anything so simple. Okay, so now this is an example that already was mentioned a couple of times in the lectures. Let's consider examples with n equal 1 supersymmetry where the cone is a non-compact Calabi-Yau space. And one example of that was actually this C3 mod Z3 cone, which I already mentioned, but it's locally just S5. So if I want to to look at some space which is not locally S5, but something more fancy, probably the simplest thing I can look at is the conifold, which was mentioned in Melanie Becker's lectures for a while. And this is just given by constraint in C4. So ZA are just complex variables, and sum of squares of these complex variables is 0. Then the good thing is that there is a lot of symmetry in this cone. In particular, there is an SO4 symmetry which just rotates the Z's. And you can write this SO4 as SU2 cross SU2. I denoted it as SU2A cross SU2B for reasons which will become clear. And then there is also a U1R symmetry which rotates all Z's by the same phase. And then, so this space was introduced by Candelas and De La Osa because they noticed that in a lot of compactifications of string theory, you can go to points in moduli spaces where locally the space starts resembling this conifold. So it plays a lot of roles in studying Calabi-Yau compactifications. But here we want to take this at face value because we want a real non-compact cone. Then one can actually derive the exact metric on the base of this cone, which for historical reasons is called T11. And it can be written as a U1 bundle over a product of two spheres. So these θ1, phi1, and θ2, phi2 label two round two spheres, and then there is an additional compact circle variable which is bundled over these two spheres. And the topology of this space is just the product of S2 times S3. So this is actually the crucial thing that makes it more interesting, because you replace something with S5 topology by something with S2 cross S3 topology when you go from the basic n equal 4 example to this conifold example. Okay, so how do we derive, for example, suppose we want to know what is the gauge theory on a single D-brane placed at the tip of the conifold. Well, let me just do it through a bit of guesswork, but I think it will be pretty convincing. So first of all, you can kind of solve the conifold constraint in terms of other variables which are denoted as A's and B's. Essentially, you can write the constraint sum of z squared equals 0 by looking at the determinant of this 2x2 complex matrix. And the determinant of this matrix has to be 0, so you just write it in a way that makes it so manifestly, namely you write this entry as A1, B1, and so on, and then you see that the determinant of this matrix is manifestly 0. So you basically replaced some combinations of z's by things quadratic in things like A times B. And then the action of this SO4 symmetry breaks up as SU2 rotating the A's and another SU2 rotating the B's. But when you did this substitution, you actually introduced some redundancy. Because obviously, if I change the A's by some complex number lambda times the A's and B by 1 over lambda times the B's, you don't change anything. So these A's and B's are not uniquely defined. But then you notice that this redundancy can just be fixed by, for example, you can always rescale, choose the absolute value of lambda so that this constraint is satisfied. And then the remaining thing, which is the phase, introduces these phase identifications. So you basically enlarge the number of variables, but then you have these additional kind of identifications. And then when you look at this, you say, aha, basically in a gauge theory, which is supposed to live on the D-brane, this looks like just U1 gauge symmetry. So this identification looks like U1 gauge invariance, where I gave to B an opposite charge to A. And this looks like just like a D-flatness condition, right? If I write down the U1 gauge theory, it's going to have a term in its potential which is just the square of this, right, times Young-Mills times the U1 coupling. Right, so basically this gives you some D-flatness condition, and this is just the gauge identification. So this immediately gives you the idea that there has to be an interacting U1 living on this essentially what you do then is you replace these A's and B's by chiral superfields. And for a single D brane, you need an interacting U1, but you also introduce, just for the ride, a free U1 because there is always a free U1. This is a kind of center of mass degree of freedom. So you basically postulate a U1 cross U1 gauge theory where the two A's have charges 1, -1, and the two B's have charges -1, +1. Then the sum of these U1s is completely free because the A's and the B's are both neutral under it. But the difference U1 is precisely the one that introduces these constraints on the moduli space. So basically you see that the moduli space is given by the values of A and B modulo these constraints, and that's exactly the conifold. So you see that the moduli space of this gauge theory is exactly the conifold. And that's the goal, right? That's the goal of, there are some more fancy ways of deriving it by partial resolutions of some higher singularities, but this looks like a good argument. And then it also suggests how to generalize this to the case of n branes, because we know that whenever you go from 1 to n, you replace U1 by UN. So the natural guess is to say that the theory on ND3 branes at the apex of the conifold is actually some UN cross UN gauge theory. And now these chiral superfields are A1, A2, and B1 and B2, which are in conjugate representations. And here you notice that I wrote, instead of UN cross UN, I wrote SUN cross SUN. Well, it's a similar story because this original interacting U1 that we had, if you want to flow all the way down to the infrared, this U1 globalizes, right? Its coupling natural will flow to 0. So this original U1, which rotates the A's and B's in opposite directions, actually becomes a global symmetry in this CFT. And in fact, it has a name. It's called Baryonic Symmetry, just to distinguish it from mesonic flavor symmetries like SU2 cross SU2. And this actually plays a big role in the dynamics of the theory, which I'll describe. But the main thing is that this is actually a global symmetry of the CFT. It starts out as a U1 gauge symmetry, but then it globalizes. And then another important fact is that to produce the right moduli space, you actually also need an SU2 cross SU2 invariant superpotential, which already figured this morning in Daniel's talk. It has the form ABAB with these SU2 tensors, which make it manifestly SU2 cross SU2 invariant. You can write this as A1, B1, A2, B2 minus A1, B2, A2, B1. Okay, so, and this passes various checks. In particular, first of all, it's a little weird that the superpotential is quartic because we're used to cubic superpotentials, at least in theories which are almost free. But this is a non-trivial kind of fixed point. So to assign R charge 2, which is the conformal value to the superpotential, we have to assign to A and B R charge 1/2. And then this actually ensures that the U1R anomaly cancels, which is a simple computation. So another way to see why you need this quartic superpotential is to compare it with the n equal 2 supersymmetric Z2 orbifold of the type that you can get from the first part of my talk. It turns out that if you take the k equal 2, namely Z2 orbifold, and take M1 equal M2 equal 1 and M3 equal to 0, then what happens is that that two of the entries in your SU4 matrix are equal to 1. So in other words, two of the supersymmetries are undisturbed by this orbifold, and this preserves n equal to supersymmetry. So it turns out that the matter content of this theory is exactly like what Daniel wrote down this morning for three-dimensional n=4 theory. There are these A's and B's, which are bifundamental, and then there are also phi and phi tilde, which are the adjoints. And then what we noticed with Witten was that if you add a Z2 odd mass term, which is trace phi squared minus trace phi tilde squared, and then integrate out phi and phi tilde, you get precisely the right superpotential. Now, in the context of ABJM theory, this happens automatically. Exactly the same thing happens. This term arises when you add Chern-Simons term to the theory. And this is what Daniel was telling us this morning. And then exactly the same argument leads you to this superpotential. So, so here is actually a problem, which this will be posted, and this is an interesting suggested problem, which looks at tracking of certain anomaly coefficients of the theory as it flows from this superconformal field theory whose dual is ADS5 cross S5 mod Z2 to this conifold theory whose dual is ADS5 cross T11. And you can actually check that this flow satisfies a lot of constraints. So I suggest you look at this problem sometime before the end of the school. Okay. So now in the remaining part of the talk, I want to consider two different. So anyone who's worked on conifolds and string theory knows that it can be either resolved or deformed, and so the two correspond to either blowing up the S2 in the resolution or the S3 in the deformation. So the deformation essentially replaces the constraint on z's by adding an epsilon squared on the right-hand side. And then, for example, if epsilon is real, you see that, and you make the z's all real, you immediately see that this is a three-sphere. This is a round three-sphere. To see a small resolution of the singularity, it's a little bit different. This is actually implemented by changing the D-flatness condition. So in the theory on a single D3 brane, you just need to add the phi Heliopolis term, which gives you this extra term on the right-hand side. So this raises a bit of a puzzle. What about the infrared theory where this U1 is non-dynamical, so you cannot add the phi Heliopolis term? But then in another paper with Witten, we proposed that actually all that this does, essentially, if you just take this same field theory and start turning on vevs for the fields A and B, you're going to cover both singular and resolved conifolds. Because if this vevs satisfy this condition with a non-zero U, they just correspond to a resolved conifold. And this can be made quite precise. So for example, suppose we take this theory with A's and B's and add a diagonal vev, say to one of the fields, say B2, proportional to U. Then, so you do this, then obviously you'll break the SUN cross SUN gauge symmetry down to a single diagonal SUN. And here is a proposal for the dual of such a gauge theory. It's a resolved conifold with an extra stack of D3 branes placed at some point and blown up to sphere. So if you want to see kind of geometrically what goes on, once you resolve the conifold, there is a round two sphere at the bottom, and then you can just put your three branes somewhere at the point. Then we know that locally, the space should resemble ADS5 cross S5. Because whenever you put branes at smooth point, very near the branes, you will grow an ADS5 cross S5 throat. So geometrically, therefore, you expect that at large R, you still have ADS5 cross T11, and now at small r, you have ADS5 cross S5. And the whole, so under the influence of adding this vev, the theory kind of changes from one theory in the UV to n equal 4 super Young mills in the infrared. And with Arvind Murugan, we constructed the full warped solution with the warp factor corresponding to this. I won't talk too much about the details of this, but it's possible to write down the exact warp factor. The hard part here is that the warp factor now depends not just on radius, but also on one of the angular coordinates. But you can see that it satisfies a lot of the checks. Okay, and this is schematically how this holographic RG flow works in this case. One way to see why you should get this ADS 5 crosses 5 with dual n equal 4 super Young mills is that if you take a quartic superpotential AB, and say add a VEV for B, for one of the B's, then you'll end up with a cubic effective superpotential like ABA. And it turns out to be exactly the cubic superpotential of the n equal 4 theory, because the n equal 4 theory has a cubic superpotential. So basically it all hangs together, but we essentially see that you don't really get a new theory. You just get another sort of CFT in the infrared in this case. Now, what about the deformation? That turns out to be a more interesting story, which is so intricate that people to this day are still trying to sort out various subtleties. It turns out in this case you get confinement, dimensional transmutation, Seiberg duality cascades all in one place. And it turns out to be extremely intricate. The trick to actually get the conifold to deform is you essentially want this S3 to kind of not to shrink to 0 size. And the way to force it is you, in addition to n d3 branes at the tip of the cone, you add m d5 branes wrapped over the S2. And the flux of these d5 branes actually pierces this S3 and kind of prevents it from shrinking. And this is the sort of basic intuition, but then it takes some work to actually try to construct the ansatz for the 10-dimensional geometry dual to the situation with extra d5 brane flux, which is a 3-form flux. And this was a program I worked on in a few papers and completed it with Strassler, essentially, where we found the warped deformed conifold solution. It again has a warp factor, which is a function of the conical coordinate, but now ds6 squared stands for the Calabi-Yau metric of the deformed conifold, which luckily is still known in perfectly explicit form in terms of hyperbolic functions and so on. And this, I gave you a reference to a review. If you're curious about its explicit form, you can read it. So ds6 squared is the metric on this deformed space. And you can ask a question, what happens if you by hand force epsilon equal to 0? I'll show you that bad things happen. Basically, you're not allowed to do that. It's a little bit like taking QCD and saying that you send lambda QCD to 0. It doesn't really make sense. But the really interesting thing is that when you solve for the warp factor, it's given by this sort of explicit integral formula. The warp factor, unlike in ADS space, it doesn't blow up in the infrared. It actually reaches a constant value. And if you drop a string to, say, t equal to 0, the string tension no longer goes to 0. And that means you retain a finite string tension, which means that there is confinement in the theory. So let me basically show you how I want to show you the comparison of warp factors. So this is the ADS5 warp factor, just 1 over r to the 4. This obviously blows up far in the infrared. This is the warp factor in the proper solution. Okay, it behaves nearly like in ADS space and then just stabilizes, which means the theory is confining. And this is the theory if you just by hand force it to have epsilon equal to 0, if you forget to deform it. In fact, in a previous paper that I wrote with Seitlin, we didn't realize that we have to deform it, so we found a solution which turned out to have a naked singularity because the warp factor just kind of turned around and hit 0. So then we realized that once we deform it, the UV part is the same, but the theory kind of gets cured in the infrared. And if you will, this really proves confinement in this theory, because this is a kind of unacceptable thing where you forgot to confine or forgot the chiral symmetry breaking. And this is how the geometry tells you that confinement really happens. So it's sort of a proof of dimensional transmutation in this particular example. Now, so as you heard from Melanie's talk, there are also some imaginary self-dual fluxes that one must add, and they must have some specific form to preserve supersymmetry. And then you find that the solution is basically non-singular and has small curvature everywhere, provided G string M is large. So M is the number of flux units of the 3 form, and G string is string coupling. So there is a limit where supergravity kind of solves this confining gauge theory, similarly to how supergravity solves n equal 4 super-Yang-Mills for large G string n. Now, if you look at the UV approximation where you can ignore the deformation, the solution simplifies, and you see lots of logarithms. You basically see logarithmic RG flow. So it turns out this quantity B2, which is the 2-form flux through the 2-sphere, it basically measures how the difference of 2 gauge couplings flows as a function of R. This agrees with the study of beta function so essentially on the gauge theory side, what you've done is you replaced the conformal SUN cross SUN theory by a non-conformal SUN plus M cross SUN theory. Then there is no more balance in the beta function. There is no cancellation, and the beta function for the difference coupling becomes of order M, and you can compare the coefficients of the beta functions between the gravity and gauge theory, and you see that they're equal. But an even more bizarre effect, which Melanie mentioned, is that if you look at the 5-form flux, that itself behaves logarithmically with radius. And we're used to thinking about 5-form flux as some effective number of D3 branes, or effective D3 brane charge. So how do you explain that the number of colors itself effectively decreases? And what Strassler and I realized is that this is really due to Seiberg duality, which is an n equal 1 supersymmetry phenomenon, which essentially, if you take, in its simplest manifestation, if you take SUNC gauge theory with NF flavors, it's equivalent to SU NF minus NC theory, provided NF lives in a certain conformal window. And this is actually the case for this theory because this theory actually exhibits a highly intricate set of RG flows. There is a very detailed exposition and review that Strassler wrote, which mainly is devoted to understanding this duality cascade. But in a nutshell, what happens is that if you look, for example, at SUKM cross SUK-1M theory, the SUKM coupling becomes very strong. And then to continue flow to the infrared beyond this point, all you do is you just carry out the duality, the Seiberg duality transformation on this gauge factor, and it sends SUKM to SUK minus 2M. But then the miracle is that the theory is completely self-similar. After the duality transformation, it looks the same as before. So that's basically the magic, that some theories can undergo these kind of quasi-periodic flows. So the reason it's so is because the number of flavors at each step is carefully arranged to be related to the number of colors. So SUNF minus C is SUK minus 2M, and then the resulting theory has completely the same structure. So what happens is that you can see that you can iterate this kind of flow until you reach the place where k is of order 1. And then something non-perturbative has to happen. There will be some chiral symmetry breaking that happens. And far in the infrared, the theory very much resembles n=1 supersymmetric gluodynamics, but with somewhat exotic matter content. So this I already showed. Another thing that demonstrates confinement is that you can compute actually the quark-anti-quark potential as a function of radius in this theory by studying the holographic calculation. You basically place Q and Q bar near the boundary and then let the string kind of dip down to the infrared. And when the quark and anti-quark are far separated, the string will just go to the tip of the conifold, where the string tension is minimized, and this gives you linear potential. So you see that the potential is linear at large distances, while it's coulombic at short distances due to the fact that far in the UV the space is anti-de Sitter, nearly anti-de Sitter. So qualitatively it's similar to what people see on the lattice in QCD, but it's certainly a much simpler calculation to just find the semi-classical shape of the string. On the other hand, it's not QCD, it's only a kind of distant cousin of QCD. Yes?
In the graph of the duality cascade, what was eta? Eta, what's the meaning of that?
There is another coupling that actually the flow, I don't want to get into this, but there is another coupling that flows from large to small values. And this is what Strassler explained in his review. Okay, so let me just summarize the infrared behavior of this duality cascade. Essentially, what happens far in the infrared is that you get to k equal 1, and then the theory is SUM cross SU2M. This is the infrared theory. It exhibits dimensional transmutation, namely the logs that you saw far in the UV got transmuted into this epsilon parameter of the deformation. And the pattern of R symmetry breaking is the same as in the SUM gauge theory. Namely, those who, the supersymmetric gluodynamics with SUM gauge group has anomaly-free Z2M symmetry, which is then broken to Z2 by gluino condensation. And the same pattern happens here. And you can even compute the gluino condensate and so on in this theory. So another interesting thing is that this theory secretly actually has baryonic condensates. In fact, if you look carefully at what happens in the lowest cascade step, the SU2M gauge group has an F equal NC, which is the point as shown by Seiberg years ago. This is where there is a kind of quantum deformation of moduli space. It turns out that that classically there are these baryonic order parameters you can write down such that classically A times B equals 0, but at the quantum level A times B is equal to some non-zero value. And this gives you a so-called baryonic branch of the theory where basically you can dial the baryon by some complex number and the other baryon down by the same complex number. It's essentially the equation curly A times curly B is equal to constant. But the crucial thing is that once you get vevs for these curly A and curly B, then the U1, this baryonic symmetry that I talked about early on, is actually spontaneously broken. And this means that the spectrum of the theory contains a Goldstone boson and also its massless scalar superpartner. In other words, it's a little bit like QCD, but the analog of pion is this Goldstone boson that you have here. Now, what are the spectrum of bound states in this theory is just given by the spectrum of fluctuations localized at the bottom of this throat, and it takes some work to extract the spectrum. But then it turns out some detailed investigations do show that not all of these bound states are massive. There is actually a massless bound state, which is precisely the Goldstone boson of this baryonic symmetry. Okay, so you can prove that there is this Goldstone boson, and this actually leads you to this whole moduli space, the baryonic branch, which are called resolved, warped, deformed conifolds, whose geometric description is somewhat more complicated. Like the metrics become more involved, and so on. And I think then it sort of drifts into more of the seminar than a summer school lecture, so I will refrain from describing these more complicated solutions. But let me basically end by saying that all of this provides you with a pretty detailed understanding of a class of 4D large N confining gauge theories with n equal 1 supersymmetry, and all kind of broad brush predictions agree with earlier results about n equal 1 gauge dynamics. Plus, you get a much more detailed information. For example, you can compute the full global spectrum, bound state spectrum, the ratios of all sorts of, can compute string tensions and so on. So for one thing, it can be used as just some kind of model, perhaps a cousin of n equal 1 supersymmetric gluodynamics, because it has the same sort of rough features. But then it also has been used in model building. For example, in warped string compactifications, this long throat with warping has been used to generate small scales. And another interesting thing is that it also provides with a setting to study metastable SUSY break, supersymmetry breaking. This is not something I'm going to go into, but if you place some stack of NTD3 branes at the bottom of the conifold, it was shown by Kochru, Pearson, and Verlinde that this actually gives you a metastable state for some range of parameters. So there are a lot of kind of further things that one can do with this story. And of course, we would like to understand further generalizations of these type of cone branes or other things with the hope to get as close to real world as possible. So I think I'll end here. Okay.